Welcome to today's webcast, How Modular Open Systems Approach or MOSA initiatives are driving new system capabilities, brought to you by Military and Aerospace Electronics Online. I'm John Keller, Chief Editor of Military and Aerospace Electronics. Today's event is sponsored by Elma Electronic in Fremont, California, Reflex Photonics in Kirkland, Quebec, and Crossfield Technology in Austin, Texas. This presentation will explore the Fiber Optic I/O and its applications in OpenVPX and MOSA-driven open standards architectures. It also will address chassis and system management for platforms aligned to the Sensor Open Systems Architecture or SOSA standard, including modular and dynamic chassis management approaches. Our presenters today are David Rolston, Senior Technology Advisor at Reflex Photonics, Gary Hanson, Staff Systems Integration Engineer at Elma Electronic, and Terry Hewitt, General Manager of Products at Crossfield Technology. This presentation is live and interactive, so you can submit questions at any time via the Ask a Question area in the user console. And the PDF and other resources are located in the Event Resource section directly under the Questions area of the console. That PDF will be available after the webcast. After our presenters finish, I'll open it up to questions from our online audience and for discussion among the panelists. First, a couple of housekeeping details. If you're running pop-up blocking software such as the Google Toolbar, you'll need to disable it to view this webcast. In addition, we recommend that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It also will be accessible from the homepage at www.militaryaerospace.com. PDF copies of the presenter slides will be available within 24 hours on this web page's Events Resources section. So let's get started with David Rolston, Senior Technology Advisor at Reflex Photonics. David?
Thank you, John. Good afternoon, everyone. Thank you for tuning into my presentation. I'll be talking about optical transceivers and optical fiber connectors for VPX, backplanes. And just full disclosure, Reflex Photonics was acquired by Smith's Interconnects about 3 or 4 weeks ago. I'm actually reporting to what's called the Emerging Technologies Research Group based out of Stewart, Florida. But I'm here in Quebec, in lovely cold Quebec right now, and I'm happy to be with you. So I'll start, excuse me, by introducing just this general idea of trying to merge optical connections, optical fiber connections with VPX chassis, or actually chassis in general. There's been a growing effort over last many years, maybe a few decades, of trying to figure out the best way of integrating optics into backplane chassis. I think that the VIDA standardization group, VIDA.com, has done a spectacularly good job of building a standard environment for this. And basically, their intentions are to add to their repertoire of tools to put optical connectors alongside the backplane connectors inside of these chassis. The next slide is really just an overview of electrical signaling. So one of the reasons for doing this at all, for looking towards an optical solution, is simply that as data rates get higher than, say, around 10 gigabits per second, as they're moving towards 25 gigabits per second, the difficulty in transmitting electrical signals over any reasonable distance, I write in here 0.01 meters, 10 centimeters, so 4 or 5 inches, becomes progressively more difficult, challenging in terms of keeping its signal integrity there, but also in terms of how much power you're using to decipher or decode or just open the eye diagram of the electrical signal, hence the idea of optics. So the optical solution, its main motivator has been usually to get optical or to get signals between chassis. It's become a little bit now towards between boards themselves. And as I said before, as SerDes port rates increase, so far Xilinx Vertex chips can produce roughly 32 gigabits per second as a SerDes speed. They've become exceedingly challenging to route along the boards, even with materials like Megtron and Rogers. So the optical solution is to bring an optical transceiver up towards and next to the high-speed performing chipsets and use fiber as a transmit to receive interconnect, as you can see in the photograph on the right. I'll be talking today about two specific things of where these optical transceivers might go in this type of configuration. There's a third one. So the first one is primarily this backplane idea where the transceiver gets to be placed right up against the backplane. The midboard, which is a transceiver that can be placed anywhere in the area of the plug-in card. And then, of course, there's the front panel, which has been there for many years now. And I won't really discuss this one, but I'm sure most of you are aware of front panel optics. To just give a quick high-level view of the optical VPX backplane idea. So it's a standard being developed within VIDA 65 and 66. There are basically four types of apertures that we can use. The apertures come from other VIDA specifications, such as the 66 and the 67. Primarily, they've been used for apertures or openings in the backplane for RF connectors. But we can use the same openings within the backplane for the optical connections as well. The photograph is thanks to Elma. That's one of their backplanes that includes optical and RF connections in it already. And then the light green cartoon is a call out of each of the particular size of apertures from 67.3 and 66.5 and 66.1. The backplane positions, so this is only representative. I've only included the aperture of the 66.4, but basically it's just to try and describe where these apertures can go within a 6U backplane. Normally it's in the position, the J2 position for the 3U portion, and then the J3 to J6. But I have to highlight here that the open apertures can actually be combined. You can have bigger ones, but generally speaking, they're pitched at 14.4 for a half width opening with a half width transceiver that I'll show you in a minute. So that's just to get the distances and placement of where these holes can actually appear in the backplane. This is a bit of a cartoon to sort of describe the two options a little more clearly. There is the first option, the top one is the cabled or midboard transceiver, and the bottom one is the backplane transceiver. They both have pros and cons. So simple explanation of the pros and cons is that the top one has the ability to place the transceiver anywhere near and as close as you want to the main ASICs, providing the data, so an FPGA or a processor, a GPU, something like that, and then stranding fiber from it over to a connector at the backplane, a passive connector at the backplane. This implies, though, that there's area taken up by both things, because now you have the transceiver area and you have the backplane connector passive area. And the one on the bottom, though, although it now has to be pushed up against the backplane, which means the electrical distance increases, so maybe a little bit more difficult to deal with the the signal integrity, but remember you're only going a few inches here. But then you gain on the fact that you only have now the area required by the transceiver module itself. Except in these two cases, one case, optics is a fussy thing. You need to tend to align these optical connectors. The fiber to fiber alignment has to be probably somewhere in the area of plus or minus 5 microns, which is down near 1/10 of a thousandth of an inch. So they're very small and need quite a good alignment to get the signal through. So in the top case, it requires a floating head on the line card and or on the plug-in card, and a fixed head in the backplane. Whereas if you change it around, you have the fixed head on the line on the plug-in card, and a floating head in the backplane. This is an example of the 66.1 and .4. TE is a big player here and has produced a lot of passive interconnects that can be a lot of optical fiber channels can be put into these connectors, but it's like the top case of the midboard transceiver requirement. The active connector, the backplane connector, is just a quick 3D diagram of how it would go together. You have the floating head on the right side. It can move in vertical or in X and in Y. And in green, the plug-in card is pushed at the MT, the optical interface, with a certain pressure to make sure they make good contact. And here also the channels can be 4, 12, 24, and support channel rates up to 25 gigabits per second so far, with the full intent to go faster. These are backplane transceiver examples. So the photographs on the right are actually the style A and the style C. They are transceivers that require, at this point, they require an electrical connector to mount them to the board solidly. And then there's a few others that involve hybrids of optical, RF optical, and active optical. So these are still being developed, but everyone seems to be very keen on these solutions. This is just a quick picture of a 1U, 1-slot representative backplane. In the inset picture on the left, you can see the 2 style A transceivers with the yellow arrows pointing at the fact that they are going to slide in and mate with the floating inserts that are in the backplane. The side view, there's a cross-sectional view of how it's mated. So on the left side, the module is firmly joined to the plug-in card using, in this case, it's an LGA interposer with screw-ins from the bottom. You can follow the electrical path in red that goes up into the transceiver, gets converted to light, and then shoots out the transceiver into the fiber as it heads to the right. You can see the spring also system pushing on the MT optical connector, and just above the 2 gray optical connectors, there's an alignment feature that does a primary alignment of the floating insert into the module as the card is being pushed together. A couple of sets of pictures for the different flavors. So the photographs on the left are one is of SMPM RF connection combined with optical floating head. The second one is just a combination of 2 and 1 for floating heads, and then the animation or the cartoon on the right just shows different strategies of how you might want to put in these optical and RF connectors into the backplane. The last thing I really talk about is maybe cable management. So one way to deal with the cables coming out the backside of the chassis is that you can either strand them, you can go off to another machine, you can cable them up with rugged cabling, but there is also the idea of cable management within the chassis itself. So this is just an example of many different variations of this can be made. But it's an example of a fully optically interconnected mesh that would link 12 12 plug-in cards through an all-passive optical fiber mesh that's been placed in the back of the chassis. So a lot of different versions of cable management we can envision. The last slide is really the summary. It just sort of says that the application is really what drives the choices for the selection of these modules. So the first thing that drives it is then what type of transceivers do you need? Do you need it all active? Do you need RF? Do you need passive optical connections in there too? That then drives the types of inserts that you would need to mate to the particular types of transceivers. Those inserts would then have to fit into faceplates that would be mounted in the backplane apertures. And that is sort of a very high level, but that's basically the way that these pieces will come together from application all the way to specifying what you need from a company like Elma. So I thank you very much for your attention, and I look forward to any questions you might have.
Okay, thank you, David. Now we'll hear from Gary Hanson, Staff Systems Integration Engineer at Elma Electronic. Gary?
Okay, so hi, I'm going to discuss the chassis manager. In general, the SOSA chassis manager has benefited from several different standards, including the VITA, PICMIG, and IPMI specifications. So today I'm going to provide a basic overview of the evolution of the chassis manager into what it is now in the SOSA system. Okay, so the primary function of a chassis manager is to discover all the FRUs that are within the chassis, to monitor the sensors that are on each one of the FRUs, and to report or repair any abnormal or failed sensors. Examples of a failed sensor would be, or abnormal, would be where you're reporting fan failures or clogged air filters. You could adjust the fan speed due to an overtemp or undertemp condition. You could also report or shut down a system due to an over or under voltage or an overcurrent condition. So in SOSA, the SOSA Snapshot 2 requires compliance to VITA 46.11 Tier 2, as well as host Tier 2, which also calls out the VITA 46.11 Tier 2. And so the VITA 46.11 calls out actually the chassis management specification from PICMIG 3.0, which is the ATCA specification. So the shelf management specification from ATCA then also calls out the PICMIG 2.0 compact PCI system management specification, and PICMIG 2.9 then furthermore calls out IPMI, which is the Intelligent Platform Management Interface, as well as the IPMB, which is the Intelligent Platform Management Bus. So the IPMB is actually an enhanced I2C bus, whereas IPMI is the messaging protocol that communicates across the IPMB. And so the basic components of the chassis management across the bus would be the BMC, which is the baseboard management controller, the IPMB, and the IPMC. So the chassis management specification for PICMIG started in the early 2000s. And that started with PICMIG 2.9, which is the compact PCI chassis management, which primarily focuses on maintaining inventory, logging events, as well as monitoring some sensors. PICMIG 2.9 only has 18 IPMI commands that it requires, though there are several optional IPMI commands that you could support. And then moving on to the PICMIG 3.0 or ATCA. ATCA greatly expanded on the PICMIG 2.9 registry information. They added several required sensors along with power management, cooling management, and E-keying. So when an ATCA system first starts up, the chassis manager communicates across the IPMV to every board in the system, gathering power requirement information from each board, cooling information from each board, as well as port routing information or requirements for each of the boards. So the shelf manager will then also read a chassis through file, which is located on an EEPROM that's on the backplane. And so this EEPROM will tell the chassis manager how the backplane is routed. It will tell the chassis manager how much cooling it can provide per spot, and it'll tell the chassis manager what the total cooling capacity for the entire chassis is. Furthermore, the chassis manager will also provide, the chassis manager will read the EEPROM and gather the power information, power per slot, and total power per the chassis. So the chassis manager then will compare the chassis routing information, the cooling information, and the power information, and will compare that to what the boards need and decide whether the boards can start up or not. So a standard ATCA system will not function without a chassis manager or shelf manager. So then moving on to the VITA46 chassis manager. VITA46 adopted several of the requirements from the ATCA shelf manager, except it did not include the power or cooling management or the E-keying requirements from ATCA. So the primary function on the VITA46.11 chassis manager, VITA4611 adopted several requirements from the ATCA, except for the power and cooling management. The primary function of the VITA4611 chassis manager is to inventory the boards that are in the system and to manage the sensors within the system, to do system configuration and recovery and diagnostics in case of any failures or faults. VITA4611 also supports 2 levels of IPMC, which would be Tier 1 and Tier 2. And so in the host specification also added a Tier 3 level to the IPMCs. And the Tier 3 specification from host adds component registration or registry information that would list all the components from the different vendors that conform to Tier 3 and to the VITA47 environmental classes. However, the SOSA and VITA4611 do not have the Tier 3, at least at the moment. So as I mentioned, SOSA Snapshot 2 requires chassis manager to be compliant to VITA46.11 Tier 2 and host Tier 2. And host Tier 2 also calls out the VITA46.11 chassis manager. So the main portion or the base portion would be the IPMCs. And this portion of the FRU, this is the portion of the FRU that connects the boards to the chassis IPMV. This represents all the FRUs, the devices on each of the boards. The IPMC is the lowest level of physical management within the or within the VPX system management architecture. This term can be applied to either a physical or logical entity, but it could be, the IPMC could actually be on an FPGA, or it could be on a separate microcontroller. So that is all on my side. I appreciate your listening and look forward to questions. Thank you.
Okay, thank you, Gary. Now let's turn it over to Terry Hewitt, General Manager of Products at Crossfield Technology. Terry?
Hi. Well, thanks for everyone for being here, and also I want to thank David and Gary for allowing me to join them today and talk about what I think is a major new effort that's going to make MOSA really happen, and it gets the value out of it that we want. And I'm not going to talk as much about what is, but more about what I think should be. So let me get started. The National Defense Authorization Act defined the MOSA objectives as, well, they're right there, and I wanted to thank the Air Force Lifecycle Management guys for letting me steal part of their slide. So, acknowledgement that this right away that I grabbed some information from those guys. And it's very straightforward, right? The significant cost savings or avoidance is the goal number one. Second goal is schedule reduction and speed of capability in the field. And this is really about how quickly a new capability can be deployed on a mission. I think the next two bullets are really just kind of reiterations or how you might get to the first two bullets. So I think the goals are very straightforward for MOSA, and I think it makes a lot of sense for for the U.S. military to be focused on these two goals. I guess my thoughts were that, well, yeah, you can do this if you have very tight standards. Then you can ensure interoperability, which allows all kinds of competition and significant cost avoidance, and you can piece things together to get some new capability in the field pretty quickly. I think that very tight standards do allow that. The problem with very tight standards is that it reduces the number of programs or missions that their objectives can be satisfied, and that leaves a gap, right? And so we want most of the objectives and programs to be satisfied, but really tight standards kind of get in that way. The converse of that is very flexible standards, which would cover a broad number of programs and missions, but clearly that misses the goal of reducing cost and time to deployment. So the real question I've got here is, where's the middle ground, and how can we bridge this gap to make things more, to meet the objectives in these types of organizations? I want to point out that there are many standards out there, and again I want to thank the Air Force Lifecycle Management guys for this slide. There's many standards out there, and they're not all the same. Some of them cover different areas, and so please don't assume when you look at this that all these are just trying to repeat each other. Some of them are software centric and protocol centric, but there are many standards, and they are converging. I think they're, a real fundamental thing I'll show you on my last slide is coming up, the Tri-Services Open Architecture Interoperability demonstration, which really says that these standards are converging, but they're not there yet. And so what do the hardware vendors do? How do they solve this problem of many standards and this flexibility versus tightness of spec? And how do they deliver components that meet the program objectives, but still they follow some standards? Well, our hardware vendors aren't dumb, folks. They've been doing this for years, right? They build a highly configurable device, okay, and it goes out the door as multiple different products, okay. And I, the little diagram here says it goes out the door as 15 different SKUs. They delay, and they've designed their device to configure it as late as possible in the manufacturing flow, and this is a well-known and many companies have this capability and are doing this today. The problem is those SKUs are not interchangeable in the field. Okay, so therefore the number of spares has to go up, the number of, the knowledge you have to know which particular SKU to make it work in this chassis or with that environment or this program, all becomes very dependent, which delays, how quickly you can roll a new mission out and, deploy a new mission. So you may not believe me, so I'm going to give you a little example here, and I want to apologize for, using one of our marketing slides and just changing the question. But the question is, if I have a very simple device, how many different ways can it be represented? Well, here's a very simple device. It's got two M.2 SSDs on it, fronted by a PCI Express switch going to the expansion plane. And it's got an optical port going to, the P2B position, which, David talked about earlier in the 3U. That's all it is. This device is not very complex, okay? Two SSDs and a PCI Express switch. Well, how many different ways can it be configured? Well, our estimate right now is it's over 20,000 possibilities, okay? Some of these configuration capabilities come from, well, there's a electrical Gen 3 connection on the expansion plane. There's an optical connection that's Gen 3. Oh, wait a minute, both of those could be Gen 3 by 4 instead of Gen 3 by 8. So now I got 4 ports to deal with. How many ports are upstream? How many ports are downstream? Where are the SSDs assigned to which upstream port? Oh, are there any in-band management ports? Are there any standby management ports? So any component out there that the expansion plane is provided to the expansion plane through a PCI Express switch has huge number of possibilities and how it could be configured. Clocks can either be internal or external. I'd also point out that clocks could be either bus or they can be radial distributed. However, when we go down that path, radial takes different termination than bus, so therefore it's not going to be the exact same piece of hardware. So all SKUs can't be solved, okay, with configuration, just some of them. NVMRO currently has different timing characteristics between SOSA Snapshot 2 and some of the VITA standards. Which one are you following? Which one does your customer follow is a real question. And so far, we've discovered at least 5 different definitions of G-discrete. All these things combined lead to a component that could have 20,000 different configurations or 20,000 different SKUs. Now, I'm not going to suggest that all 20,000 of them are meaningful, but 20 for sure are meaningful. And that becomes a real problem with that many different SKUs of the same thing out in the field. And by the field, I mean either at the system integrators or at the repair depot or actually deployed in the mission, okay? All those things fall in that definition of field. So with 20,000 capabilities, and given that first slide I showed you, I could have 20 different SKUs. What do we really want, okay? What we really want is that same highly configurable device, okay, to be shipped to the systems integrator as a small number of SKUs, 2 or 3. And let the systems integrator decide how to configure it more for the particular program or chassis or chassis. And so they'll come up with a few SKUs. But and then as you get it deployed to the field, in this case, which is the maintenance depot or the actual mission, many SKUs don't show up out there because there's still some capabilities that can be reconfigured in the field. Not all capabilities can be reconfigured in the field. You certainly wouldn't want someone to reconfigure it during a mission such that the plane went down. So there's some caution here, right? But how much of the configuration you want to push all the way out to the field, but there's certainly a lot of configuration you'd like to have in a maintenance depot. If I've got one component that can go into 4 different systems, just configured differently, I've just made a huge savings and spares at the maintenance depot. So this is what we really want, okay, is to how do we do this? And so, I want to explore the possibilities of how we do that. Because what it delivers, as we look at this next slide, right, is currently you have a highly flexible device that becomes, you look at the green line on the without dynamic configuration, it drops off. The systems integrator gets very few configuration capabilities. They buy different SKUs, but they're not configurable. And the maintenance depot has even fewer possibilities, and the mission has almost zero possibilities. And the difficulty does get easier. That's just simply because you have fewer choices, okay? You can't do, so the difficulty line comes down in today's world, but it's still more difficult than it is flexible. And what you really want is a world where the flexibility line comes down, but it's better than the difficulty line, like the graph on the left. So with dynamic configuration, yes, you have capabilities in terms of flexibility are reduced at each step, getting all the way into the mission, because as I said, some things you don't want to be able to change in the mission, but the ease of getting to those configurations is significantly reduced. And I'd say, okay, well, if hardware vendors can do this, why is it that this is not, capability is not out there today? Well, to deliver this capability to the field, what you really have to do is combine the IPMC functionality that Gary mentioned with the board control functionality that everyone has on their cards, okay? And once they're in one device, now you have access to that board configuration capabilities from the maintenance port or from the IPMB interface. Many ways you can get to this device and actually tell it to change its configuration. And what I mean by the full board controller is, you would add things like power supply sequencing to an IPMC. A basic IPMC definition says you can start power supply sequencing, but you don't actually sequence each power supply as it comes up or deal with resets other than start and stop. Okay, a lot more depth has to be put into that device to enable it to do power supply and reset sequencing for the whole device. The things I already talked about, right? The clocks, the expansion plane configuration. And what I haven't mentioned is FPGA programming. If you've got an FPGA on your card, which most cards are, maybe most is, a lot of cards are going out the door today with FPGAs on them. You can give them completely different images that could be controlled by a board controller IPMC combination to provide totally different functionality. Anyway, so I think you get the message that if you combine these IPMC and board controller into a single device, now you enable that slide 2 slides ago where you can actually delay the decision into making the SKU until later in the process, which reduces cost and reduces time to delivering new programs to the field, which is fundamentally the objective of MOSA. This slide is maybe a little bit gratuitous, but just to point out, I'm not just talking and saying, hey, this could be done. We've done it on 4 different boards, okay? These boards have an IPMC that is completely controllable by the system manager or a task manager talking through a chassis manager to reconfigure the device. So this is not just theory. It's one that we've actually have up and running. And that's all been enabled through combining, an IPMC functionality with the board controller and doing it and, in a way to provide the programs, missions, and products with these highly flexible capabilities. So we've done this through some other tools we call these generators. Okay, The concept here is that you don't want to be messing with low-level code in order to provide a new function. If you have to go in and mess with very low-level code, now what you've done is opened up this whole bag of verification worms that you have to avoid. So you control these capabilities, through commands you built into the IPMC or to controllable things that can be verified in advance. Okay, that these different configurations will work. So to wrap this up, I just want to say we're going to be demonstrating this with Elma, Bellman, Concurrent Technologies at the Tri-Services Open Architecture Interoperability Demonstration in January at the GTRI facility in Atlanta, Georgia. This is the day after Embedded Tech Trends. So it's, we think they'll have a really good audience, and it's a great thing. Come down to Embedded Tech Trends, come on over to GTRI the next day, and we're not going. This is not going to be the only demonstration there. So the TSOA-ID.com website is a great place for people to go to get information and to register and that type of stuff. But Crossfield and Elma and Bellman and Concurrent will have a demonstration that's focused on this, dynamic reconfiguration and showing it actually happening in real time as a live demonstration. To wrap up with that and say thank you for listening, and I hope the talk caused you to think about how we should be doing things in the future.
Okay. Thank you, Terry. Now it's time for questions from our online audience. As a reminder, you can ask a question at any time via the Ask a Question area in the user console. So I've got a question here. It's a fiber question. Are these fiber connectors impacted by high G or high vibration environments?
Great question. So we have done extensive testing with sine vibration sweep, mechanical shock, random vibration, all based on the MIL standard 1344. We've got, it's a shame I thought about putting a slide in about shock and vibration testing, but I kind of kicked that one out at the last minute. But yes, we've tested all these things as well as salt and fog. We've tested it with high temperature conditions. So the operating conditions of the transceivers are from the most aggressive transceivers we have from -55 to 100 C. That's a hard one to get to 100 C. So I prefer to go to 85 C, but we can do it. Hope that answered the question.
Okay. How do the goals of MOSA differ from SOSA? And aren't both standards trying to achieve the same goals? Who'd like to take that one?
Hi, this is Terry. I'll be happy to take that one. I think the first thing to point out is that MOSA is not a standard. MOSA is the modular open system approach as defined by the National Defense Authorization Act, I think in 2017 or 16, somewhere back then. Okay, so MOSA is an approach that it's an umbrella of a bunch of standards, which I showed a number of them on that one slide, and you can pick up the slides and see them. There are differing standards. I mean, SOSA is sensor open system architecture. Okay, and there's a set of standards there that heavily leverage VITA with some extensions. And from a hardware perspective, there's also software standards and architecture standards that are very similar to FACE or leverage a lot of the FACE stuff, but they're kind of a full sensor open system architecture approach. HOST is from NavAir, Hardware Open System Technology, and it leverages off VITA, and much of it has been adopted as a starting point for SOSA. And CMOS is CERDEC Modular Open Systems I can't remember the last. Sorry, these are the hardware standards. But I will point out that the host team, the CMOS team, and the SOSA hardware team are very actively working together. Okay, so you might find some differences in those three standards, but they're going to be smallish, and hopefully they can be covered by this reconfigurability capabilities that I mentioned. I will point out that the 4 boards that I described are also, or I showed a picture of, I didn't describe them. They're all SOSA, host, and CMOS compatible, and yes, some of it has to come from reconfiguration.
Okay, I think this next question might be for David, and that is, are the fiber connectors impacted by temperature?
Yeah, good question. So we have done extensive testing on temperature cycling, on thermal shock. We actually have some of our devices going into satellite type applications, so a lot of aggressive temperature shock and cycling there. The connectors, having said that, I mean, the connectors are still optical. They you need to set them up properly and need to make sure things are properly heat sunk, and but they're fairly resilient, and we've done a lot of active live testing over temperature as well. So there you go. Hopefully that helped answer.
Okay. What would the limitations on data rate of copper signaling be? In other words, is there a minimum data rate speed where optics becomes essential?
Yeah, it's a very hard question to answer, because every time someone puts a line in the sand saying copper can't do it past that, somebody else figures it a way to go faster and do it across the line. So I would say the biggest issue with that optics solves really is trying to minimize the amount of total power consumption while giving you the distance. So instead of being able to only go over, a few inches, now it lets you to go over a few meters, and allows your system become a lot more diverse and flexible. But actually, sorry. So I would say anything. I would say anything over 25 gigabits should target optical.
Terry, I want to kind of second what David said and add to it that, I'm one of those guys that's old enough that I have actually predicted the end of some technology, and that's an extremely dangerous thing to do. I believe that David's prediction of 25 gigabits is reasonable, but I also will bet anyone a beer that wants to bet me that that there'll be someone that comes up with a logical answer that gets noticeable beyond that.
Okay, we've got a follow-up to are the transceivers affected by temperature question, and that is, what is the range of temperature involved?
Yeah, so we typically do active testing, so we're sending live traffic through the modules while they're being thermally cycled. Our typical thermal cycling range is -40 to +85, although we have been asked to push that range. I believe I can say with some confidence we're at -55 to 100 Celsius, but like I said, it's very hard to get those to work. And so part of the issue in getting them to work is that the laser, the detector behave differently at different temperature ranges. So you have to do this dynamic juggling act of changing its operating settings to get into different modes. But totally confident between -40 and +85, and then with some good bit of hand holding ranges higher than that.
Okay. Can existing backplanes with RF be retrofitted with optics?
Yeah, actually, they can. It might be a little bit of tinkering with your screwdriver and everything, but yeah, the backplanes that Elma produces, we've used in different ways and fit our optical parts in there. So that's fairly good. And the standard, like I said, in the Vita is aiming for this backwards compatibility too, but do realize that you actually have to unscrew your backplane from your chassis and tinker with it a bit.
Yeah.
Okay. Has there been any testing for environment or temperature done on these parts and interconnects?
Yeah, well, I mean, I think I answered that in the other questions, but I'll just quickly reiterate. So yeah, like we've done extensive testing on humidity, fog, vibration, shock. We've actually even interesting enough, we've done a lot of radiation testing. We've gone to Texas A&M, used their cyclotron, and bombarded them with ions and all kinds of things like that to see and set effects. So types of, whether they suffer from long-term damage with gamma rays and things like that. So we're just going crazy with testing around here.
Okay. Can you define Tier 2 in the host and Vita 46.11 standards?
Well, I get, this is Gary, and I guess the easiest way to describe the Tier 2 would be somewhat to compare it to Tier 1. So when a system is first powered on, any Tier 2 boards that are in the system will send out a statement to the chassis manager stating that I am here and this is my address, whereas a Tier 1 will just sit there and wait until the chassis manager goes out to pull the different addresses that are listed in its FRU file that tells it what addresses are available. So a Tier 2 board will start up whether the chassis manager knows that there's anything at that address or not, whereas a Tier 1 will only respond if a chassis manager requests information from it.
I'm assuming
okay,
that responding there is still the low voltage 3.3 volt
yes,
aux
yes.
kind of thing, right?
Only when, with the 3.3 volt aux.
All right. Well, I think we've come to the end of our questions. Is there anything that our audience has forgotten to ask? Anything that you gentlemen would like to add to wrap up and sum up? I'll take that as, no, I think we've covered everything. So, on behalf of Military and Aerospace Electronics and Endeavor Business Media, I would like to thank David Rolston, Senior Technology Advisor at Reflex Photonics, Gary Hanson, Staff Systems Integration Engineer at Elma Electronic, and Terry Hewitt, General Manager of Products at Crossfield Technology. This presentation will be archived within 24 hours and can be accessed from the Military and Aerospace Electronics homepage at www.militaryaerospace.com. A reminder email message for the archive will be sent to registrants with a link to the archive, and the PDF of the slides should be available later on today, if not earlier, right here in the resources section of this user console. So we thank you for joining us today. I'm John Keller, Chief Editor of Military and Aerospace Electronics.